Dear friends, welcome to the 2020 Löwdin Symposium held here at Uppsala University in Uppsala, Sweden. Every second year, we invite two prominent scientists to Uppsala to give the so-called Löwdin lectures. So far, some 31 scientists have been awarded this honorary title, Löwdin Lecturer. This year, we continue the tradition and welcome two new lecturers. Professor Nancy Macri, the 2019 Löwdin Lecturer, and Thomas F. Miller, the 2020 Löwdin Lecturers, to the family of Löwdin Lecturers. We look especially forward to their presentations, which will be the last presentations at the respective days of the symposium. The Löwdin lectures are made possible through a donation in association with Professor Löwdin's retirement in the early 1980s. The aim of the donations was to promote the chemical science in general and to establish a contact with the students with respect to the topic. In association with the Löwdin lectures, we also have the Löwdin Symposium. This year is a bit different, however, due to the COVID pandemic. The whole event this time is facilitated as a webinar. However, there's nothing bad that doesn't bring something good. This year we have in excess of 480 registered attendees from all around the world. This is a new record for the Löwdin Symposium. You are all very welcome, and I'm very pleased that you could join in. To all of you, I say good night, good evening, good day, and good morning. The theme for the symposium is usually a hot topic of the time. Last time, it was machine learning and quantum chemistry. All presentations were recorded and are today available at YouTube. This time around, however, we have no hot topic. Rather, we will celebrate that it's 60 years since Per-Olof Löwdin, by royal decree, was appointed the professorship in quantum chemistry here at Uppsala University. We have invited new and former Löwdin lecturers to talk about their science. This to get a full picture of the impressive width of the field of quantum chemistry. A large number of the former Löwdin lecturers responded positively to our request. Some got their honorary title some 24 years ago. Thus, during the next 2 days, we will listen to some 16 lectures, 8 each day. They will cover topics anywhere between electron structure theory and molecular dynamics. They will be devoted to subjects as different as the structure of the periodic table, interstellar chemistry, or the intriguing dance of protons and electrons, just to mention a few. My name is Roland Lindh, and it's my pleasure to be your host and moderator for the event. You are all welcome. To help me and you with the technique, we have some assistants behind the camera. Join me to say hello to Jesper Hansen and Patrik Lindström. Hello. Before we start, some logistics. Each day is divided into 3 two-hour sessions, altogether 6 sessions over the whole symposium. Each session includes 3 lectures, apart from the last session each day, which is composed of 2 lectures. Each presentation is 35 plus 5 minutes for questions. We kindly ask all the attendees to post your questions through the Q&A option in Zoom. And I'm urging you to post your question there while the lecture is going on and not to start to type them when we come to the Q&A at the end of the lecture. Finally, the whole symposium is recorded and will later be made available on our website. For scheduling details, we kindly ask you to consult the website. Some last-minute changes have taken place during the last day. In particular, I would like to point out that Rod Bartlett has replaced Leticia Gonzalez, and that is a change that's going to reflect the first session today. And for tomorrow, I would like to get you to notice that the time slots of So Hirata and Martin Quack has been swapped. We also direct you to the symposium website for the abstracts of the presentation. At the website, we have also material, that is papers, photos, and interviews, etc., related to the fantastic scientific life of Per-Olof Löwdin. Before we start, I would also like to tell you that if you're experiencing any technical problem with the Zoom webinar, we urge you to leave the seminar and log in again. Most of the problems will be solved that way. So with all of that said, it's time for us to start with the first session, in which we're going to have presentations from Rod Bartlett, Wolfgang Domcke, and Pekka Pyykkö. So I welcome Rod Bartlett to the webinar. If I understand it right, Rod will also say some words about Per-Olof Löwdin. So please, Rod, could you share your presentation with the rest of us?
Hello, I hope I can. Yeah, you're talking about teaching old dogs new tricks. I had never done this before.
Well, nice t-shirt.
It's colorful to wake everybody up. It's on my side of the world.
Splendid.
All right, so I need to share screen. Okay, and here it is. Okay.
Here we go. Something started.
Right.
Yes.
Okay.
Could you go to full screen also, please?
Excuse me?
Could you go to full screen too?
Green, so you need to get from this where you're on this slide. How you when you start your slideshow? You do here, Ron. Just do PowerPoint like you do PowerPoint.
Yeah.
And then do it. How do you normally show it? There.
Is that better?
That's better.
Okay. All right. Well, I picked this topic both because we've done a lot of work with it recently, but also because it kind of ties together these 60 years of work that Löwdin did and taught many of the rest of us. In my particular case, I joined QTP about 5 years after its inception. And after leaving for 10 years, came back and joined the faculty. So I guess I've been associated with Löwdin and the Quantum Theory Project at Florida for something like 45 years. The development of coupled cluster theory has been so powerful in our field that we can make all kinds of predictions now of heats of formation and structure and spectra of molecules with confidence. Yet the most applicable tools are what you call single reference coupled cluster theory. In other words, you devised algorithms that allow you to do these things very efficiently and get excellent answers most of the time. But of course, there's always some approximation involved. Now, assuming that you have dealt with the basis set and a reasonable level of cluster expansion, what the other thing that matters is what some people call a multi-reference character. I think this mainly comes from the philosophy of CI, because it's easy to do multi-reference calculations in CI. So they prefer to think about things like biradicals, in terms of at least two determinants and other things on top of that. Whereas a single reference method basically means you're using one of those two determinants to start your calculation. So this is an inherent error that's going to be, in principle, present in any single reference coupled cluster calculation. All right. Well, let me start with a few words about Löwdin. Needless to say to this audience, he was an extraordinary human being. Very energetic, constantly teaching all of us quantum chemistry in various guises. And I will make a few comments along the way too about that. He of course, after he got this lectureship in Uppsala and started all of that project, he came over to Florida because Löwdin liked the idea of spending the winter in Florida and the summer in Sweden. So in 1961, he started the Quantum Theory Project. And of course, we had winter institutes in Latin American schools. And of course, he was doing summer institutes even longer than that. There they are with these infamous water polo games there on the right side. And these schools were where a generation of quantum chemists learned about linear algebra, as he would say, linear algebra and perturbation theory. This is perturbation theory 1 to 14. All of you are familiar with wave reaction operator perturbation theory, partitioning technique, and such things. He also worked hard on the quantum theory of many particle systems. In this case, we're talking about density matrices, and here is the nth of the Q density matrix. Here's the first order reduced density matrix, gamma 1, where I would use a lowercase gamma in what follows in this discussion. And of course, this allows you to define natural orbitals and their occupation numbers. So here he is with this particularly attractive picture showing you just some of his honors. All right. Now this talk really starts in about 1959. The correlation problem in many electron quantum mechanics, advances in chemical physics. And of course, this is a journal or a series of books that he initiated as well. And he points out that a wave function approximated by a single Slater determinant is usually a rather poor solution to the Schrodinger equation. It's instead turned out that phenomena depending upon the individual motions of the different particles are of almost as much importance as exchange phenomena. and that a better treatment of many particle systems can be obtained only if this correlation between the individual motions is in some way taken into account. So he pointed out, 1959, the correlation problem is today, therefore, of crucial importance, not only in atomic, molecular, and solid state physics, but also in nuclear physics. All right. So that's kind of where we start. And I think all of you also know this, or have seen similar slides, that from the beginning in Löwdin's work, he was pointing at the full CI. Of course, there was no hope of getting there for anything but very, very small problems, but he was thinking about it as a reference point, as the culmination of quantum chemistry in a basis set. So here you have that single determinant I was talking about, with 4, in this case, doubly occupied orbitals. Then you start taking single excitations from it, all possible singles, double excitations, all possible doubles, triple excitations, quadruple excitations, and so forth. And if you get up to n-tuple excitations, you get to the full CI. So you put all of those determinants in a wave function of enormous dimension and solve the equations, and you get the full CI. And that's the reference point. That's what we're shooting for. Now, the alternatives to this are to use perturbation theory. This is many-body perturbation theory, and I think it's really a misnomer to call these things Merler-Pleasant perturbation theory, because there's a fundamental difference. Many-body perturbation theory means that these methods scale properly with the number of particles. Ordinary perturbation theory does not have that property. It would behave like CI, would not be size extensive. But perturbation theory is order by order. If you want to go to infinite order, you use the couple cluster generalization. So you have CCD, CC singles and doubles, with triples, with quadruples, and you get the full CI. All right, so this just gives you a little bit of the dimensionality of this problem in terms of numbers of occupied and virtual orbitals. And you see that something like CC SDTQ or CI SDTQ, single reference, is into the 6th. Into the 10th, as we usually say. But coupled cluster theory itself has lower scaling. So we can do many more calculations if we don't have to go all the way to this into the 10th. And that, of course, is the great property of coupled cluster theory. Here, the number of quadruples would be 10 to the 12th, for example. Number of triples, 10 to the 9th. For a modest example of 10 occupied orbitals and 100 virtuals. All right. I don't think it's adequately appreciated that Löwdin, pointing to the full CI limit from the beginning of his work, is likely the person most responsible for the current philosophy of ab initio quantum chemistry. And I would define this philosophy as pick a basis set, define its full CI, compute the correlation correction, and hope you can get close to the full CI result. The last 60 years have been devoted to its effective solution. All right. Now, single reference coupled cluster theory and its equation of motion extensions arguably provide the best answers for the largest number of CC accessible. I mean by that, there are things you can do with DFT, of course, that you can't do with coupled cluster theory in quantum chemistry. And the question is why? Most importantly, correct scaling with size, extensivity. Rapid convergence to the full CI, that's our objective after all. Higher CI excitations decomposed in terms of lower clusters. T4 being C4, quadruple excitations in CI, that end of the 10th quantity I talked about a minute ago is C4. C4 is decomposed into a T2 squared plus a T4. And T4 you can ignore frequently, but the T2 squared is absolutely essential. That makes the scaling into the 6th instead of into the 10th. And then you have the EOM CC extensions of coupled cluster theory to do excited states, ionized states, things like that. And it's very importantly intensive for energy differences, because when you're talking about an excitation energy, it's a local phenomenon in some molecule. So you need to have those relative energies accurately reproduced as well. So all of this starts with what's called many-body perturbation theory. And the reason it's many-body is that the correct wave function for a molecule, this goes to infinity, the correct wave function for a molecule is the sum of link diagrams based upon a resolvent operator and the Hamiltonian raised to the kth power. So the energy of MBPT comes from just putting this into the Schrodinger equation, projecting from the left by phi naught, and you get E naught plus E1. Typically that, if you start with Hartree-Fock, this is the Hartree-Fock energy. Then you get the second order energy, third order energy, and so forth. All right. And the critical element is that these are all extensive, because if you limit yourself to link diagrams, those are, they guarantee that the numbers you compute scale properly with the number of particles, meaning you can treat infinite systems, solids, and polymers. In these perturbation theory papers I referred to a minute ago, Löwdin talked about the link diagram theorem in PT5, as we would refer to it. But he never actually used the fact that the energies, order by order, had to be represented by only link diagrams. That was first observed by Bruckner and Goldstone and defines proper size extensivity, a fundamental property that should apply to all quantum chemical applications. Now, the next step is the transition to coupled cluster theory. We've got the same wave function, but here it's written in terms of this expansion in R naught H to the kth, subject to link diagrams. But we can replace that whole expansion there by writing the wave function. This is what Löwdin would have called this, the wave operator, pardon me, is what he would have called it, as exponential t. Exponential t working on some vacuum state, Hartree-Fock type determinant or something, gives you the CC wave function. And t is split into 1 particle effects, 2 particle effects, 3 particle effects, and so forth. And you say that t is connected. It has to be connected so that products of t can be disconnected, of course, but the total wave function has to be linked, and that's the way you ensure that it is. All right. This observation was originally due to Hubbard, but followed by Koster and Kummel, and Chisholm and Paulus were the first to derive the CCD equations. And that is an enormous step forward. Of course, from there, you go on to do CCSD, and you add triples, getting the so-called gold standard, CCSD parentheses T, and you go on to quadruples. You go on to EOM-CC to do excited states, and you evaluate density matrices, as we will get to in just a minute. So this is the relative convergence for a bunch of full CI, small molecule examples, usually with small basis set. This is some measure of the difficulty of the calculation. So here's second order perturbation theory, third order, fourth order, fifth order, sixth order. And you see it's converging toward 100% of correlation. Here is the CI. This is CI singles and doubles down here. You add triples and you go there, and that's not really converging. By the time you go to CI with quadruples, it looks like it's converging, but that's misleading. That's because these are small molecules. In many cases, they don't have more than 4 electrons. So that would be the full CI. But if we're talking about some complicated system, whereas this blue curve will continue to converge to the right 100%, the red one will be down here someplace. All right. In fact, you can prove that the correlation correction with CI is going to be 0 for an infinite system. But better than just using perturbation theory is this green curve. This is coupled cluster theory. So here is CCSD. You're already at 90, 80 something percent, 90 something percent, I guess. And you come up here, now you're at about 90, with triples, about 95%, and quadruples, you're essentially there. And this curve will stay there because of the extensivity. It will not behave differently, assuming you have adequate basis sets and all of that, for any number of electrons. So what's the only potential criticism of single reference coupled cluster theory? Using a single determinant reference to build a wave function, what I was calling the vacuum determinant. Fermi vacuum determinant. All right, and as I said, that's mostly conditioned by years and years of people doing CI calculations and multi-reference CI, and the fact that it's relatively easy to do that in CI, but it's hard for us to introduce a linear combination of determinants in place of that one vacuum determinant in the sense of wide applications of coupled cluster theory. Because we assume that if one can compute CCSD parentheses T and so forth from suitable basis set, that the single reference CC answer is assumed to be right, except, because you can always throw this in, often nebulously defined multi-reference effects. But there are no multi-reference effects at the full CI. So if single reference CC is close enough, the potential multi-reference effects are accommodated. So that's really the goal when you think about single reference coupled cluster theory. The intent of this talk is to try to quantify the residual multi-reference effects. So we start with the density matrices. So these are not the CI density matrices that Löwdin wrote so much about in his 55 papers, 1955 papers. These are the coupled cluster density matrices. They're response density matrices because they basically come from considering the energy derivative. You don't have a normal wave function like you have in CI where you can write down psi star psi. So what you have to do instead is write your expectation values in terms of a quantity lambda, which is a de-excitation operator that you solve for in coupled cluster calculation, along with the e to the t that you solve for to get the wave function. The two together define first order properties. And clearly it is not symmetric. Down here, this is the solution for T. This is the coupled cluster equation. Here's the solution for lambda. All right, but you can do this. This is routine. I assume that every CAN coupled cluster program out there, this is part of the calculation. And so these density matrices should be routine for such calculations. All right, once you have that density matrix, you can diagonalize it. And this, of course, is what Löwdin taught us many years ago. It defines natural orbitals, U, and their occupation numbers, N. Okay. And here's an example, and I don't want to drive you nuts with a lot of numbers. I hate people that show tables with numbers, but just look at the extreme limit here. What I'm showing is the convergence to the full CI for all of these different methods. And you see that the coupled cluster theory gets there pretty quickly. But this is the BH molecule. The first set of numbers is at equilibrium. This is at a stretched geometry, and this is at a highly stretched geometry. So it makes it more and more difficult to get to the full CI, but you see the comparative convergence. So the point is these coupled cluster approximations, single reference, are giving you perfectly reasonable set of occupation numbers where the occupied one, here you can see the occupied ones, 1.99, 1.95, 1.85, and then you have unoccupied orbitals with a little bit of occupation. These are the virtual orbitals for the problem. And you see how those can grow a bit as you start stretching the geometry. So your occupation numbers are telling you, look out, you're beginning to get an effect, a multi-reference effect here. And here's an extreme case where you have gone all the way to 6 angstroms, I believe. Now, the other thing I want to show you is that it doesn't matter. Here is Hartree-Fock. Here is Bruckner. This is a Bruckner determinant coupled cluster calculation. Here are the natural orbitals from a CCSD calculation. Here is some DFT. It happens to be QTP00, one of ours, but any kind of cone sham set of orbitals can be thrown in here. And here is CAS SCF. And you will see there's there's no appreciable difference depending on what the orbitals are. And I think that's extremely important when you start talking about you want an index that's going to apply to all your problems that means something. You can't have an index that's going to vary with orbital choice. Well, one of the powerful things about coupled cluster theory, of course, CCSD, is that these orbitals are all, the results, the CCSD results are insensitive to orbital choice. So you don't really have to worry about it much. So here, if we go ahead and do a UHF, now you have an alpha and a beta, but you get the same behavior, except that you got to compare two numbers, the alpha and the beta block. And here, it's much easier to get to the 6 angstrom result than it is with RHF, as anyone would expect. All right, as the fundamental invariant in the system, we want to use the density matrix to define suitable indices to assess multi-reference character that remains in a single reference wave function as one of its sources of error along with basis and cluster truncation. The density matrix is extensive, extensive, here I'll write down a few of it, size extensive, so that the index will scale correctly with the number of electrons. It's invariant to orbital rotations in the occupied and virtual space. It's able to respond to changes in a molecule with geometry, as in bond breaking and transition state. It's size intensive for state differences, which helps to distinguish between multi-reference character within a cluster and the units themselves or between different electronic states. And it's able to assist in separating required combinations of determinants for particular spin combinations and low spin states of molecules for more fundamental multi-reference flow. And this is another aspect. Single reference coupled cluster theory for open shells is very hard to, you do not get spin eigenfunctions. So you have to pay attention to the expectation value of S squared to monitor that. Other properties that are helpful is the one I just showed you, insensitive to orbital choice. It doesn't matter much what the orbitals are. Once you're doing at least CCSD, and it gets better as you add triples and higher. And it, surprisingly maybe, it's insensitive to basis set choice beyond a reasonable level. All right. So the first thing that we introduce is the variance. So we're talking about the ideal single determinant. It has n electrons in it and is describing all n electrons. We don't need any virtual orbitals. It's kind of an interesting concept to think about. To measure the role of occupation numbers in virtual orbitals, we define a variance, which is this occupied density matrix, trace of it, minus the square of the density matrix. That's the variance. And this, of course, its trace is just the sum over I, the number of occupied electrons. Notice that this is not sum over Ni quantity squared, but Ni each individual. Now, we also define something we call external electron number. And that's the same kind of summation, but instead of it being occupied, it's over virtuals. Notice the A there. So this is the extra electron number. The number of electrons that are in virtual orbitals that are not accommodated in a single determinant. And we can play around with it and see that its variance is written here in terms of EEN, but now normalized over the number of electrons. That's what I call XEN and a correction term. So now we introduce 30 examples, 15 single reference and 15 multi-reference molecules. And if you have time to look at this, the XEN, the renormalized EEN, and the variance are very similar for the single reference cases. They're not so similar when you go to the multi-references. And that's the intent, you want to be able to measure this multi-reference effect. And I guess roughly speaking, you can look at them in detail, but roughly speaking, the variance is about twice as big for the multi-reference example as it is for the single reference example. By the way, what we mean by a multi-reference example in this case would be something like, here you go, excuse me. here you have C2 at 5 angstroms, for example. Well, here's a better one. N2 at 5 angstroms is this value for the variance, whereas N2 at equilibrium has that value for the variance. Okay? So it is doing something for us. Here's a better way of looking at it. So these are the three quantities we've introduced. Here's the variance. Here is the EEN with the normalization factor. And here's the EEN all by itself. These blue lines are all by itself. And notice the scale here is quite different. This scale is about 100 times bigger than that one. So if I took everything on this figure, it would fit in halfway up to 0.5. Right? So that shows you the relative magnitude of the multi-reference effect. So here's another. But we found out that in addition, we have to pay attention to the individual orbital occupation numbers among the virtual orbitals. Here is what happens when you have single reference. And here we just got a bunch of molecules indicated by color. And as a function of the natural occupation number, and you see they're all well below 0.1. In the multi-reference case, that's not true anymore. They go up to 0.5. 0.5 would be the typical situation, be H2, for example. H2, the HOMO and LUMO have to be 50-50 in a single determinant description. In an RHF description, that's not possible, but it is possible in UHF. We'll get to that in a few minutes. So you see the indication of multi-reference. Now, if you plot all of these things as a function of the frequency of occurrence, you get what's called the probability distribution function. And you look at it, it looks like a delta function. Here it is on a log scale, which shows the variation a little bit. But the reason for showing this on the normal scale is that we want to take the cumulative distribution function, and we see that it will be some kind of a heavy side, because a delta function integrated gives you a heavy side distribution. So here it is, cumulative distribution function, and that's its algebraic form right there. Okay. So now we add up all of those occupation numbers to find an I, and then for convenience, we take the negative log of I and the hyperbolic tangent to define a new index. This is our third index now, the multi-reference index. And you see, and it's now set up so that if it's negative, it's a multi-reference problem, these orange X's. Single reference is blue. So if it's positive, it's single reference. If it's negative, it's multi-reference. All right. So we can take our 30 species again and show what happens with this MRI value. And you see that everything we call single reference has a positive MRI. And everything we call multi-reference has a negative MRI, just as we would have anticipated. And that's more informative now than the variance, because look here, this is a very small variance for this MgO molecule. So why in the world would we say that it is multi-reference? Because that tells us that. So we started paying attention to just the largest occupied natural orbital, virtual orbital, and actually the second largest, and we get plots like this. Again, you see the scale is very different. So the largest one is blue, and it's going up to something less than 0.05. And then orange would be another, the second most important occupation number. And then you go to the MR test set, and now this is all of these fit into this red band. But now you see how many of these exceed that. And here is our MgO and Vn and Ben minus, which are ambiguous examples from just the variance, but tend to accumulate because of the nature of their LUMO and LUMO plus 1 orbital. If we look at this in detail, we can see that using this number, 0.0337, we get 100%, well, excuse me, I guess here we get 99.73% of the correct answer for all of our examples. All right, we call this the NON, the natural orbital number. If we go to 0.058, we get 100% of it. See, there's a couple of places where you do not get truth. Here's one, and here's one. If you stop at 99.7%. All right, so here's kind of my final example. These are diatomic molecules, and we have written them in terms of a variable here. Excuse me, let me go back. So we could put them all on one scale. So these are the singlet states of all of these molecules. At the CCSD level, if it's R, it's restricted. If it's U, it's unrestricted. And you can see all the curves. Here's N2, you know, with its hump up here. And so you can now, but notice that N2 unrestricted, the dash one, see, of course, behaves itself perfectly well, as we all know. The others aren't quite as dramatic. Here, I guess this blue one, F2, is a little bit dramatic between the two, the RHF and the UHF reference. So here are the actual indices as a function of this R variable that we introduced. And here are the RHF examples. Here are the UHF examples. And you see the qualitative difference that you have. There's still noise at the bifurcation region where RHF changes to UHF, but then it settles down and nicely converges to the right answer. So we have several other examples in our paper, which I'll leave to you to read. H8 has been called an example for multi-reference couple cluster theory or strong correlation, which I wonder about a little bit. Anyway, we studied it. We studied the transitions, activation barriers and so forth in bicyclobutane and the biradical phenylene dinitrene, open shell singlets, alkaline earth oxides, and several other examples. So some of these, you know, will still have multi-reference character according to our indices once you have even switched to UHF. But this is what normally happens. Here's single reference. Oh, excuse me. Here's single reference. Here is the multi-reference set I talked about. And here is the UHF multi-reference set. Notice they have all gone away. All these complications have gone away. So the first thing anybody should do is if they're going to use a couple cluster calculations to do problems where they're concerned about multi-reference effects, they certainly use UHF reference. And you can do it with about the same time and trouble as you can with an ordinary RHF reference. So we were able to define four indices: the external electron number, the variance, MRI, an analysis of the distribution of the virtual occupation number, and the NON is the single largest virtual orbital occupation. We calibrated it by just, you know, not 30 examples, but at least they were consistent, and we knew they were genuine multi-reference and genuine single reference. And we had a clear distinction. We observed that most multi-reference examples are made effectively single reference, which an RHF is replaced by a UHF. And the residual multi-reference character subject to UHF references, which can still persist, as I said, in that biphenyl dinitrene, for example. Recommend alternative approaches to standard, like EOMCC, tailored, what we call tailored, our lambda, CCSD parentheses T, or actual multi-reference methods. But recognize that the number of genuine multi-reference examples is far less than anticipated by most work. Okay, that's it. Thank you.
Thank you, Rod.
Yes, thank you.
Thank you. Very, very interesting. I see here we have one question in the Q&A for you.
Right?
I'll read it. It's from Yuri Aoto. So, hi, Professor. Do you expect that an index such that these can be used not only to separate single reference and multi-reference cases, but also to quantify the missing correlation energy and add to single reference couple cluster energies as a correction?
Well, we certainly intend for these things to help quantify what we're calling multi-reference effects. As I said, it's nebulous. I think if these indices prove to be useful in the long run, or certain modifications of them, they may attain the status of being quasi-predictive quantities. So in that sense, you would begin to be able to address that question.
Okay, thank you. If you go to the Q&A later, you could actually type in an answer to this question. If I not have this, okay. Also, I have a question. So I know you've been advocating couple cluster theory, and I come from the school of wave function theory, but there's always this constant comparison with DFT theory. So from your perspective and experience with couple cluster theory, what would be the strongest arguments for using couple cluster theory, and what is its weakest point?
Well, I think most people would say its weakest point is the single reference, CC. But the reason for using couple cluster theory is it's a many-body theory. It's a correct many-body theory. You can treat polymers and solids and so forth. You cannot do that with CI. As I mentioned, the CI correlation correction is 0 for an infinite system. That's not true with many-body methods like couple cluster theory. So ultimately, the field has to recognize this and gravitate toward doing things in as rigorous a manner as possible. And that's the many-body approach. Now, it's not just couple cluster theory, it's not just MBPT. We can throw some propagators in there maybe too. But the point is that these have, their properties are critical to an accurate description of electronic structure that CI does not accomplish.
Thank you very much. For those of you who are attendees, you could still write your questions in the Q&A, and Rod might go and attend those and answer those in written form, apart from the live presentation here. So with that, Rod, thank you very much. I know it's early in the morning, so thanks for the effort.
Thank you, Roland.
You're welcome. You're welcome. So with that, we move on to the second presentation for this session, which is by Wolfgang Domcke, who's going to give us a review of the field of wave packet dynamics at the conical intersection and the developments that have taken place there in that field during the last 30 years. So with that, I ask you, Wolfgang, if you could share your screen with us, please. Good morning, by the way.
Good morning. Can you see something?
Well, I can see you, certainly, sir.
At the moment,
Oh, here you come. Yes, I can see your presentation now. Yeah. If you could go over into full screen mode, please.
Yes.
And you will have our attention until 20 minutes past.
Yes. Okay.
You're welcome.
Okay. First of all, thanks, Roland, for putting up this great meeting in difficult times. We appreciate very much your efforts in getting those together. Now, my talk today is a little bit of personal talk, personalized talk. I over a time scale of 30 years, I cannot cover everything, every important contributions which have been made to wave packet dynamics. Yeah? So I apologize to those whose contribution I cannot mention in this talk. I will start with a very short introduction about conical intersections. Of course, most of you are familiar with it, but let's go step by step. It goes back now nearly 90 years to a paper by von Neumann and Wegner, who defines the conditions for crossing or non-crossing of potential energy surfaces in molecules. And the argument basically is very simple, and you can follow it here. So in the vicinity of a two-state crossing, and assuming that the Hamiltonian is real, valued, you have to fulfill two conditions. They have a degeneracy. A1 has to be equal to A2, and B has to be 0. Two conditions. Now, in a diatomic molecule, you cannot fulfill two conditions with one coordinate, but in a polyatomic molecule, of course, you have many degrees of freedom, and then it's easy to fulfill this condition. So it's basically a dimensional argument. Yeah? And because we have to fill two conditions, we can characterize all conical intersections in principle by the so-called two-dimensional branching space. So by two vectors in nuclear coordinate space, which defines the conical intersection. So this was known now 90 years ago, but for many, many years, for many decades, it had very little impact on chemistry because it was too abstract. There's one exception, what we call nowadays symmetry required conical intersections are conical intersections which exist because of the high symmetry of the molecule. And the well-known case is the Antelope Effect. The simplest case is the so-called E cross E, the Antelope Effect, a doubly degenerate electronic state and a doubly degenerate vibrational mode. And when you sketch the potential surface, you see this is the famous Mexican hat. You can see it is a highly anharmonic, non-trivial potential surface generated by the Antelope Effect. But this was studied since the 1930s and has developed very well. The first paper wherever a rigorous spectrum has been calculated was by Higgins and co-workers in 1958. By matrix diagonalization, they got a spectrum of such a Yantella case, and you see it is a double hump, and very roughly, the first hump corresponds to the lower part of the surface, and the second hump corresponds to the upper cone. So this was one extreme case. The other extreme case is so-called no symmetry conical intersections. This is actually the von Neumann-Wegner case. So there is no symmetry to require a conical intersection, but nevertheless, they exist. And incidentally, in the same year, in 1990, both Mana and Iaconi and Rüdenberg and co-workers, they found such conical intersections in helium H2 and in ozone. And this requires highly accurate multi-reference, multi-configuration, multi-reference calculations, because to be sure that you have a conical intersection, you have to compute the wave function around a loop of the intersection. And if the wave function changes the sign, then you know you have encircled a conical intersection. So we require really accurate calculations. This is the reason why it took so long, until 1990. Now, I should mention in organic chemistry, there was a very prolific team, Rob Bernardi and Oleguchi, which in the 1990s discovered many, many conical intersections. And since then, there's general agreement that conical intersections are everywhere in somewhat larger polyatomic molecules. But in between now, there's a wide space of conical intersections, which we nowadays call, following David Iaconi, symmetry allowed conical intersections. And I have sketched here an example where the ethylene cation, and we stumbled across these intersections in the late 1970s and the early 1980s. And this is one of the first examples. And it's actually a very simple mechanism. if you take a molecule like ethylene and you take the CC stretch coordinate, which does not change the symmetry, you may have intersections between electronic states of different symmetry. Yeah? There is nothing special about it. However, if you lower the symmetry, in this case, it's a torsion of ethylene, this becomes a conical intersection. And this is sketched here. Now, this is the so-called what we call tuning mode, yeah, and perpendicular to it is a coupling mode. And in general, you have an avoided crossing here, but when you come now to the point where the intersection is, you get a conic intersection, yeah, and then it's lifted again. And in 2 dimensions, it looks like this. So this is a very simple mechanism to generate conic intersection, and it turned out to be a very important, very efficient tool to find them ab initio, because you just had to do calculations ab initio along tuning modes, and when you find crossings, you had to find out what are possible coupling modes, and this produces conic intersections. This led us in the 1980s to a model which is still used today, and which nowadays called the linear Bibonic coupling model. And this model, on the one hand side, it generates conic intersection, and on the other hand, it provides a very simple Hamiltonian, which can be used then for rigorous calculation of spectra and dynamics. And this is shown, Hamiltonian is shown now here. I'll explain it very briefly. So you have a reference Hamiltonian H0 for your number n of electronic states, whatever you have of electronic states. This is the unperturbed Hamiltonian, which belongs to the ground state. This is just a multidimensional unperturbed harmonic oscillator. But in the excited state, you have now this coupling operator W, and the diagonal elements of it contain the excitation energies and the gradients, which are the intrastate Bibonic couplings. And the offline elements, n and prime, they contain now these coupling modes Qi with coupling constants lambda. And it turns out that these kappa and lambda can be computed very conveniently with ab initio calculation. And this brought, so to say, Bibonic coupling theory to the ab initio world. And now with this Hamiltonian, the way is open to do now in a very straightforward way calculations of spectra and time-dependent dynamics. Now in wave packet theory, we do time-dependent dynamics. So we solve the time-dependent Schrödinger equation with the molecular Hamiltonian Hm. And in general, or in the simplest way, we do it by expanding the total wave function capital psi in electronic states psi n, whatever they are, and in vibrational basis functions, or alternatively in grids for each nuclear degree of freedom with coefficients. In any case, you get a very simple numerical problem, first order differential equations for the coefficients, which you solve in time. The first wave packet propagations in molecular dynamics were done by Veit and Fleck in the very early 1980s, and nearly simultaneously by Kozlov, using the so-called split operator method. And a bit later, Tal Esa and Kozlov proposed the Chebyshev method, which is very efficient and is still used today to do such wave packet calculations. Another example is the iterative Langevin method by Park and Light. So these different methods don't make a big difference. Yeah? The problem is the dimension of your Hilbert space grows exponentially with the number of degrees of freedom. Yeah? And we come back to this later. But this is the only fundamental problem here, that your space, Hilbert space, very quickly gets very large. Otherwise, it's a very simple numerical problem. So for this example of the ethylene cation, we calculated the spectrum, the Bibonic spectrum of this excited state of the cation, the first excited state. And you see, you get a very complicated spectrum. There is no way whatsoever to assign these spectral lines here. This is because of the very strong coupling of the conical intersection. It is both non-adiabatic coupling as well as mode-mode coupling by the anharmonicity. In the time domain, I think the calculation of Horst Köppel in 1983, I think was the first time-dependent wave packet calculation ever at a conical intersection. And the result is shown here. At that time, we were interested in this electronic population dynamics P of T, which is the total population in the upper electronic state, somewhat simplified. Yeah? At that time, this was a completely new concept, and we had great problems with referees to publish our papers, because at that time, people were thinking in terms of single von Oppenheimer vibrational levels, which are coupled to other tiers of levels. And the populations they consider were populations of single vibrational levels in some state, whereas this is the total population of an electronic state. And you can measure it, as we will see later, with femtosecond technology, which was not available at this time in 1980. And therefore, people were not much interested in this thing. The interesting thing is that also this is an electronic population. It shows vibrational dynamics indirectly, because at this very short time scale, there is no exponential decay. The vibrations are, the conical intersections are passed coherently, and the system is swapping back and forth the electronic populations by the coherent vibrational modes. This is a signature that the vibrational dynamics is still coherent on these timescales. Now this is now for a number of molecules. I will not review this here. Mention just one example, the benzene cation, which we started to consider in 1988, and Horst Köppel has worked a lot for many years on this problem. This is a more recent qualitative picture. And what you can see here is a beautiful model of a multi-state system with multi-vibrational modes. And if you preparate, for example, this E-excited state, you see there's a sequence of conical intersections which takes you down to the ground state. The intersection in the middle are Antella intersection. The other intersections are symmetry allowed intersections. And then for this model system with more efficient computation methods as are available nowadays, they can calculate the population probability starting in this upper excited state with probability 1 at time equals 0, go to the instantaneous preparation, and then you see the excited state decay. It goes to an intermediate state, and finally it goes to the ground state. But this is just one example which may be representative for many others, but it's maybe one of the most beautiful examples what you can do with such a very simple model Hamiltonian. Now, around 1990, we switched our interest to neutral excited states. They are, of course, much more interesting than cations because they are much better accessible for experiments. And the example we chose is the molecule pyrazine. And it was a good choice because even nowadays, it is a benchmark problem for studying non-adiabatic dynamics, in particular new methods in non-adiabatic dynamics. So pyrazine has an S1 excited state, which is an M-pi star state, and a second excited state with a pi-pi star state, very typical for other aromatics. And over time, several models were developed. The basic model involves just these two states and 3 vibrational modes, which were selected by initial calculations. And here are then the results of the wave packet dynamics. You see the population decay again, the population of the upper excited states. There is 2 states in this case, but now we have to be a little bit more precise. There is a diabatic population probability and an adiabatic population probability because we have to distinguish diabatic states and adiabatic states. I have no time to define this in detail, but you see the adiabatic state are shown here, the upper surface and the lower surface. These are the adiabatic state. So this dotted probability gives the time-dependent probability to go from the upper surface to the lower surface is a function of time. And you see everything happens within several 10 femtoseconds, some recurrences, and then it's done. And everything is more or less on the lower surface. And we also started to compute the vibrational dynamics in more detail. This is a trajectory. This is a quantum trajectory. It's the mean value of the wave packet. And you can see that even in a very small system, only 3 vibrational modes, we get fully dissipative vibrational dynamics because of the very strong coupling of the modes. And then we can look in more detail, looking at the actual wave packets. Now the wave packets are high dimensional. So to look at it, you have to reduce them. So what you do, you take the square of the wave packet and then you integrate out the other degrees of freedom. In this case, you take, for example, the tuning mode Q1 and you integrate over the other degrees of freedom. And this is the time here. This is the upper surface. This is the wave packet on the upper surface. And you see it decays within 20 femtoseconds. And while it decays, it appears on the lower surface and continues to oscillate coherently. So this is not a statistical decay process. This is a coherent transition through a conic intersection. But this is deceptively simple because when you look at the coupling mode now, you project on the coupling mode, you see the story is very different because it's a very anharmonic potential curve. And this initial wave packet is immediately squashed within tens of femtoseconds and performs a very anharmonic dynamics. And of course, in the real dynamics, these are coupled. These are just 2 different pictures of the same wave packet dynamics. Now, this linear Bibonic coupling model assumes diabatic, harmonic diabatic electronic surfaces. So it's of course limited. So we thought since a while in the 1990s, can we extend it to chemically more interesting problem? And this is one example, torsional dynamics. Assume that you have one large amplitude torsion, so you can again construct diabatic model potentials, which are periodic now in this coordinate, and then you include another few harmonic modes and a linear coupling mode, and then you get these adiabatic surfaces. And you see you generate periodic potentials with 2 cones by which the upper surface can decay to the lower surface. And Hahn and Stock modified this model to be more realistic, and this model is still used today by many simulations for the dynamics of rhodopsin, for typical photo-induced torsional dynamics, cis-trans dynamics. This is then for this model, for this symmetric model, the result. So you have a wave packet density in the excited state. It decays to the ground state on this 100 femtosecond time scale. You can look at the photophysical dynamics, which means the population of the upper adiabatic state. And you see from 1, it relaxes to about 25%. Or you can look now at the photochemical dynamics, whether you are left and right. So you start, let's say, on the left-hand side, and your initial population is trans, and then it develops in time. And after 1 picosecond, you get exactly 50-50 mixing, which means that this dynamics has completely lost any memory on the initial preparation. And this, of course, is only possible because of the conical intersection. If you would have a one-dimensional dynamics, this would just oscillate back and forth. So that the conical intersections makes the whole dynamics irreversible. Now, another example, which is quite obvious, of course, is dissociative dynamics, which would be photodissociation. And I refer here to examples which are motivated by ab initio calculations by Wolfgang and myself, where we found that in certain molecules like pyrrole, indole, or phenol, which means aromatic molecules with NH or OH groups, you have these usual pi star excited states, but you have a new type of so far unknown dark state, which is completely dissociative. And these are so-called pi sigma star state, and the sigma star orbital is plotted here. And you see this is a very unusual orbital. It sits outside of the molecule it is anti-bonding with respect to NH or OH, and this orbital is pulling away the H atom, and then, if you take phenol as an example, you get first a conical intersection with your bright state, which you can excite by light, and then you get another conical intersection with the ground state. And this state then allows a very rapid dissociative, non-adiabatic dissociation, and we will come back to more details later. And then again, we try to grasp the essential features in a simple model, which is still in the spirit of the linear vibronic coupling model, but now one coordinate is dissociative or reactive. This is shown here. This is in phenol, the OH stretching coordinate, and the second coordinate is the torsion, which is the coupling mode. And in this case, you have two conical intersections, and incidentally, you have the same coupling mode here and here. This generates a very nice problem, very, very integrated, because you generate a wave packet here. It has to tunnel through a conical intersection. So it is a non-adiabatic tunneling, which is much more involved than a typical barrier tunneling. It has to tunnel here, and then it hits the lower intersection, and this determines the branching ratio of your exit states. And very briefly, one example is here, one wave packet calculated in these potentials. So we generate an initial state with one quantum in the stretching mode, because otherwise the tunneling would be too slow. But by putting in the energy of one stretching quantum, we get tunneling on a 100 femtosecond time scale. And then this wave packet hits the conical intersection, and this happens here. So the node line switches by the conical intersection. The node switches over here, and then this propagates, and here it has hit the second conical intersection. And I think you can easily understand that this effect here, it's the first conical intersection, is a huge effect what happens the second conical intersection. This is, of course, ideally suited to control, laser control of non-adiabatic dynamics. More details will come at the end of this talk. Now, I will briefly talk about advanced methods. I started with a straightforward basic approach of expanding your wave packet in a basis, in time-independent basis. And the most widely used and well-known method, which is now advanced compared to this, is the multi-configuration time-dependent Hartree method, developed by Meyer-Mann and Cederbaum in Heidelberg. To make it very brief, the basic idea is you use a moving basis set of orbitals. And you expand your wave function by a configuration expansion in a moving basis. And this makes it more efficient, because by moving your basis with the wave packet, you need much less basis functions compared to the straightforward method. And to test this method, they invented a fictitious 24-mode model of Piracy by adding all other modes just in linear and quadratic approximation. And for this demanding models, they showed they can converge numerically the autocorrelation function, and the Fourier transform of which is absorption spectrum. So they can compute a fully converged absorption spectrum for a 24-dimensional, strongly non-adiabatic problem. A related method more recently is the so-called multiple Davidoff ansatz, developed by Yang Zhao and co-workers in Singapore. It is basically the same idea, but applied now more specifically to harmonic oscillators. It's again a variational ansatz. And more recently, Lipeng Chen in my group has applied it to a slightly different 24-dimensional conical intersection model. And it shows wave packets in the tuning mode and the coupling mode, now for such a much larger model system. Then I mentioned a quite recent development, the tensor train technology. I can do it only briefly. This is work by Victor Baptista. So you have your multidimensional wave packet now in the nuclear coordinates x, and you write this wave packet as a product of one-dimensional wave packets, which, however, are correlated by the sum over alpha. So this is just a representation which at the end leads to a very compact description of a correlated wave function. And they applied it to the same model, and they also, with this method, shows they can converge completely the autocorrelation function and the absorption spectrum. So this is another method which is very well suited, ideally suited for these linear Vibronic coupling problems. And finally, it's of course natural to extend now your model, which contains a few vibrational modes, to a bus. This could be a liquid environment, for example, or it could be all the other modes of a large molecule. So you simply take your tuning and coupling modes of your conical intersection and you couple them to a bus to introduce dissipation. And here we computed such an example now for a two-dimensional Pyracine model. This is the pure Pyracine model, two-dimensional conical intersection, and you see you get a very irregular, chaotic population dynamics without the bars. If you turn on the bars, you see quickly it gets smoother and smoother, and of course the population decays to zero because now you can distribute your energy to the bars. And interestingly, also the wave packet shows this effect. This is the wave packet of the two-dimensional problem. It's very erratic, chaotic. Once you couple to a bars, in this case a strong coupling to the bars, it gets smooth. And as pointed out by Michael Torwart, for example, you can even do the following. So here we use this hierarchical equation of motion method of Tanimura, and you can do even the following. You can take the vibrational modes of the conical intersection and put them in the bus, and then use this numerically exact HEOM method to compute the dynamics with this complicated bus, and it can sometimes even be more efficient than the other way around. Okay, this summarizes my short overview of more recent powerful computational methods. Now we can look now at all these beautiful wave packets, but of course this is not really satisfactory because they exist only on the computer. So the question is, can we also observe them in reality? So can we measure these wave packets? And this leads, of course, to the problem of time and frequency resolved mapping of the wave packet dynamics. And the mastermind in this field is Charles Mukamel. I'm sure you know him. And he developed the basic formalism for so-called third-order nonlinear spectroscopy. I've shown here two examples. One example is transient absorption pump probe spectroscopy. So you have a sample, you excite the sample with a pump pulse, and then you transmit the probe pulse, and you detect the change of the probe pulse by the pump pulse. So it's pump probe spectroscopy, very simple concept. A bit more sophisticated is so-called four-wave mixing spectroscopy. You have three laser pulses impinging the sample, and the four-wave mixing generates a new laser pulse, laser radiation in a particular direction, which is given by the so-called phase matching. And this is then what is detected. Now, using Mukamel's formalism, one can calculate the signal in a very transparent way. So you have three pulses. So you have an integral over the three time functions of the pulses, and then you have a so-called dipole, third-order dipole correlation function R, which again consists of several terms, and one of is shown here for a two-level system. So very simple, just a two-level system with some dephasing parameters. Now, what we realized early on, this is easy for a two-level system or a three-level system, but for a multi-state system with many vibrational modes and conical intersections, this is simply unfeasible. It's practically not possible. And we had to think about different ways to do it. And we developed the so-called non-perturbative method of the same spectroscopy, which conceptually is very simple. So the quantity which is really interesting or fundamental is the polarization P of t generated by the pulses. It is given by the expectation value, in this case with the density matrix, of the dipole, transition dipole moment mu. Now the density matrix you can compute with the Liouville von Neumann equation, including the field. This is now not a propagation of the molecule itself, it's a propagation of the molecule with the field. When you do this, you get P of t. However, this is not what is measured. As I explained previously, the measurement is, or is shown by this graph again, the measurement is in a particular combination of wave vectors. So you have to decompose now your total polarization, into particular components in particular directions. And this can be done in an elegant way. And when you do this, you get the P and M, and this gives you the signal. This can be called an a posteriori phase matching decomposition, because you calculate the complete polarization and then you pick out one component. This is not totally efficient, and therefore we developed later, Maxim Gelin, sorry, I'm on the next slide, Maxim Gelin and Dasha Egorova, we developed the equation. Now what's happening here? Sorry. The equation motion phase matching approach, which calculates explicitly the polarization in a particular direction, and all what you need are some additional propagation of the density matrix. I can't go into more detail now, but this really takes you now from the propagation of wave function or density matrix directly to the signal. This is the most direct and elegant way to calculate the signal from the wave function. Now I'm getting a bit short of time. I skip this transparency and show you only this more recent application for time and frequency resolved fluorescence as one example of such a measurement. On the left-hand side, this was the example we had before. This is a pyrazine with a bath. Yeah? This is a adiabatic wave packet, the wave packet in the upper adiabatic excited state as a function of time. And this is now the corresponding fluorescence spectrum, the measured quantity, or calculated on the computer. And to be brief, you can see, of course, it's not identical, but all the relevant information is imprinted in this signal. So we can observe, if we have sufficient time resolution, we can observe moving wave packets in molecules. Now I have two more slides at the end to show you some very interesting more recent results. This is work by David Giacconi and Hua Gur. And one thing they did for a model, two-dimensional model of this phenol problem, yeah, predissociation of phenol. You see here the adiabatic potential surface. They did a calculation in the adiabatic representation. All what I have talked so far, all calculations are done in the diabatic representation. And if necessary, the results are transformed to the adiabatic representation later. The calculation is much more challenging in the adiabatic representation. You can see here this very spiky conical intersection. You have to solve, you resolve in your calculation this potential surface, which means you have to work very carefully. In addition, you have here non-adiabatic coupling elements which become infinite at the intersection. So you have extremely rapidly varying, extremely spiked elements here. But if you work sufficiently hard and precisely, you can solve the wave packet dynamics with the adiabatic Hamiltonian. And the good news is you get exactly the same result as you get in the diabatic propagation. So the numeric works. Yeah? And in the adiabatic representation, you have the so-called geometric phase. And in principle, you can do the calculation correctly with the so-called geometric phase, and then you get the identical result as in the diabatic representation, or you can leave out the geometric phase, and then you see you get something different because you miss this destructive interference here. And geometric phase has become of much interest also recently. here you can say again this tunneling around a conical intersection. Usually if a wave packet and it goes this way and this way, it will interfere constructively here. However, with a geometric phase, it will interfere destructively here. And this was very nicely demonstrated in this recent application by Hua Gu and co-workers. This is now a small radical, and this is now thermal dissociation on the ground state surface. There is a conical intersection here, but it's not touched. Yeah? The wave packet goes either this way or this way, but then there's interference. And now the elegant thing is, if you do it correctly, and you measure the rotational states of your product, you only get odd parity levels. If you incorrectly drop the geometric phase, you get even parity levels only for the rotations. So by measuring the rotational spectrum, you have a direct experimental measurement of the geometric phase. I'm finished with this. And I thank all of you for your attention. Okay, can I?
So Wolfgang, thank you very much. Can you hear me?
Yeah.
Oh, great. So I have two questions from the audience. So the first one is from Shirin Faraji.
Yes.
By the way, nice having you with us. Beautiful talk as always. She starts with flatter. Could you please comment on the idea of propagating LVC Hamiltonian on the fly, namely parametrization along the trajectory? Can this address the limitation on LVC for large amplitude motions? Any advice on how to extend the model for large amplitude motion, please?
Okay. Of course, the linear Bibonic coupling model by construction is limited to small amplitude motion. Of course, there is an elephant in the room, which I did not mention, and these are on-the-fly quasi-classical trajectory calculations. And basically, in the last decade, we have a competition between wave packet simulations on one side, on given potential surfaces, and on trajectory simulations without potential surfaces, so-called ab initio on-the-fly calculations. These are competing. At the moment, I would say the favor is for the trajectory calculations. They are by far in the majority because they are easy to do. They are very expensive computationally, but otherwise they are straightforward to do. In my opinion, this will switch in the next decade, because now with machine learning, we can now, probably in the coming years, we can construct high-dimensional, complete ab initio potential surfaces. And then the calculation with wave packets is much more efficient than with trajectories where you have to recompute everything at every time step. So that's my opinion. I expect in the future, I expect that we move back to calculations of potential surfaces, which we need for wave packets, but these surfaces will be much better and more powerful than we have them now.
Thank you. I have another question here. It's from Kishan. And he asks, if the ground state is very close to the excited manifold and participates in various non-adiabatic couplings with the upper-lowering states, how can we assign the reference state? The reference state in the Hamiltonian, he adds on. And I wonder if this has to do with a theory where you actually don't need to identify which state is which. Please.
Okay, a good question. In these applications, just historically, we always looked at cases where there is a well-defined ground state which is is widely spaced from the excited states, which is practically always the case in closed shell molecules. But of course, there are challenging problems, for example, in radicals, where you don't have this separation. Then this whole concept of using a ground state reference state is not very useful, and one should approach the problem more fundamentally, rather than construct such a model and just go ahead straightforwardly.
All right, thank you very much. You can still ask questions to Wolfgang in the Q&A, and I'm going to direct the panelists to look in the Q&A and try to identify those questions that are addressed to you. With that, we move on to the third and the last presentation for this first session today. And I kindly invite Pekka Pyykkö to share his screen with us, please. How are you doing, Pekka?
Should be coming. Just a minute, yes. Now I have a full screen mode. Can you see this?
No, you're not sharing your screen with us.
Yeah, okay, thank you. Let me see. Share screen. That was share screen.
Oh, there we go, yes.
Okay, lovely. And then I go full screen mode.
Perfect. You have our attention until 2 o'clock.
Yes, 2 minutes overtime.
I will step in 5 minutes before that so we can have some Q&As.
Yeah.
Thank
lovely.
you.
So being among theoreticians, let's start with the Hamiltonian. And this here is the Dirac-Coulomb-Bright Hamiltonian. I have something on top here. Can you see the title? Yeah, okay, this is good. This is the Dirac-Coulomb-Bright Hamiltonian, which for chemists is an excellent theory of everything. And now we have one-body Hamiltonians for the electrons, the little hi, which are the Dirac ones for one electron with kinetic energy, rest mass, and the nuclear potential here. And we have the two-particle Hamiltonians, which have the electron-electron repulsion, just Coulomb's law, 1 over Rij. And we have the bright Hamiltonian, which has the retardation and the magnetic electron-electron interaction. And in correlated calculations, you should add electron-like projection operators on both sides of these two electron operator. There will be higher terms and there will be QED. And this H is actually, so to speak, 101% correct, because the higher levels of physics, meaning quantum electrodynamics, which mainly consists of vacuum polarization and self-energy, will cancel about -1% of the Dirac level relativistic effects. So let's have a test. Let's look at an atom, and for me, the normal atom in the periodic table will be gold. But the spectrum of the Dirac equation will consist of an electron-like continuum, which you have up here, which can be simulated also with a finite basis set, and it will have bound states in between, and there will be a positron-like continuum. And then if you take the lowest state of a 1s, for a point nucleus, the 1s would actually dive to the positron-like continuum after 137 atomic units of nuclear charge. But for a realistic finite nucleus, that will happen around z equals 173. So you can go much, much further than 137. And then I promised you a gold atom. let's have a look at the ionization potential and electron affinity of a gold atom. The original data were first published by this collaboration of Paszkiewka and Borszewski and Kaldor and Peter Schwertfeger 3 years ago in Physical Review Letters. And at Dirac-Coulomb Hartree-Fock level, we have an error of minus 1.5 electron volts. And then when you go to coupled cluster with up to pentuple excitations, the error goes down to 0.04. Add bright, it goes down to 0.029. And when you add the lowest order quantum electrodynamics, you have the red number over here, 3.2 milli-electron volts. And that's your error deviation between a very good experiment and theory, completely theoretical theory. And for the electron affinity, the precision is even better. This is Dirac-Fock, and then you have a coupled cluster which has a good description of the correlation. Add bright, and then with QED, you have an error term or deviation between theory and experiment, which is minus 1.4 milli-electron volts. So this is an extremely good theory, which we actually quoted in our latest review on the periodic table in Nature Reviews Chemistry this year. So this theory has the impression of working. And then if you want molecules, let's have a look at a triatomic molecule, copper, silver, and gold monocyanides, where you have very precise microwave molecular structures. And the metal-carbon distances are given up here. And we tried to calculate this as well as we possibly could, 2008, and getting the last picometer right for the right reason was not easy, but it was doable. And then when I gave this as a challenge, suggested it to Keith Peterson, it took them 5 years to do it better. And copper improved, silver improved, but gold actually became worse. You have 191 and here 190.7. And this is possibly one of the earliest examples of a QED effect seen for a heavy element molecule. There are many calculations on light, small molecules, diatomics, and so on, but this is one of the few where you can say something reasonably well documented for a heavy element. So this seems to work, and it looks like we are having a steady ground under our feet. Then how about the periodic table? Currently 118 elements up to Oganes-Son, which is OG, element 118, are known, and why don't I see? And then the question would be, what will happen after 118? And 119, 120 are being hunted at, but not found yet. And then it's an interesting question to ask. Would you have something, some new structures like a 5G, which is the bottom line here, the 5G series, which goes from 121 to 138. And I spent some time on this question. And after that, there will be Fs and Ds. Sorry, the Ds come before, Fs will come after. So there have been all kinds of studies of the periodic table an early Dirac-Slater one, fully relativistic, but only very rough density functional, was published by Fricke, Greiner, and Weber in 1971. And essentially, I cut the lowest but one very long line into pieces in an article in 2011. So starting with the periodic table in the first place, who discovered the periodic table? There were bits and pieces early on, and originally they were based on atomic weights, M, because there was no nuclear charge. Nobody knew about nuclei, so you couldn't think of a nuclear charge. And Löwdin was the first person to note in 1817 that the atomic weight of strontium is the average of those for calcium and barium. So you can hardly be more economical in science. Calculate one average value in 1817 and be remembered in 2020 for that. And then 12 years later, he had 3 other averages. The atomic weights were settled in Karlsruhe, Germany in 1860 in a big meeting, which had a 150-year celebration in 2010. And there were several attempts, of which I would lift up Mayer's 1864 book in its first edition. And he had only 28 elements, not all elements. He had a square table with gaps. He did not have all columns. He did not make any predictions. He did not use the word periodic, but he was 5 years before Mendeleev. And then Mendeleev did all that Mayer had missed, predicted scandium, gallium, germanium, and these were shortly afterwards discovered. And as somebody wrote, the Royal Society in London gave its Davy Medal to Mendeleev and Mayer in 1882, probably to the dismay of both. So both have merits. Maybe Mendeleev has somewhat larger merits, but the 5-year priority of Mayer is interesting. One more group was discovered by Ramsay in Britain, and we now call it Group 18, or the noble gases. Then you could attribute the discovery of the actinide group to Seaborg, 1945, and so far the 6D elements are boringly similar to the 5D analogs. And my small question here is the one about the 5G series. Will there be a well-defined 5G series, and where should it be? There are many reviews and histories on the periodic table, like Eric Sherry's book in 2 editions now, or the review article by Wang and Schwartz. And during the 150-year celebrations, there were conferences of ACS in San Diego and the Mendeleev 150 in St. Petersburg, and so on. And these have many collected publications during the International Year of the Periodic Table 2019. And this is my modest answer for the periodic table if you want to go up to 172. And now, after 118, which we had, okay, we had 118 over here, and then there will be 2 S elements. Everybody would agree on that, on 8S, 1 and 2, an alkali and alkaline earth. And then from 121 onwards, I would like to attribute a new line which runs from 121 to 138 with 18 5G electrons, at least formally speaking. And then we would have an F series, 6F series from 141, in between there is 139, 140, and then 141 to 155, and then we would have a D series from 156 onwards, and we would end with the 8p 3/2 element 172, as already suggested by Fricke and Weber. So here we are. That's a modest proposal for a new periodic table with a well-defined place for the 5G elements. And now many people had considered this. Where do the various shells get occupied? And if you take a screened Coulomb potential, such as the Thomas Fermi potential, Ivanenko and Larin had in 53 an estimate which gave, like Landau and Lifshitz, the non-relativistic quantum mechanics book, an answer around 124. And then at Dirac-Slater level, there is Weber or Fricke 125, and these are summarized in my paper. And now Seaborg knew about these atomic calculations and supposed that the 5G would enter around Z equals 122, but he did not put an exact, complete, dedicated 5G block anywhere. Then there were calculations in Paris by Paul Indelicato, and he said that from 143, 3 plus, you would have 140 electron systems with the exact closed shell configuration 8s2, 8p2, 5G18, which I also find at multi-configuration Dirac-Fock level with optimized levels. And that would have completed the 5G block for atomic ions. And there is very little known about molecules, but with Jean-Pierre Dognon of the French Atomic Energy Commission, we published a paper in Angewandte Chemie 2017, and we looked at octahedral assumed model systems EF6, and the 6 first electrons would be eaten by the fluorines, and a systematic 5G occupation starts from Z equals 125. And here you could think of the 4N series for trivalent lanthanide ions in compound molecules or crystals. So these are the Mulligan populations in all humility. And what you see is a purple straight line. So the take-home message, if somebody would ask you tonight, what did you learn today? The answer would be, I saw a straight purple line from 125 to 129 for the 5G populations of certain hypothetical hexafluorides. This is using the Cambridge B3 LIP and full Dirac relativity. So that's roughly all that we know about the 5G, except that we can call the 5G energy of a 1 valence electron system 118 plus 1 electrons for 0. And then, as I told you, we start with 8s1, 8s2, and the S would still be lowest here, but then we would have Ds, and we would have a couple of keys. And then from 123 onwards, the squares are the lowest, and then they would be above the straight line, which is the 5G orbital energy, from 125 onwards. So even in molecules, we would occupy the 5G. And then, then the L times L plus 1 over R squared centrifugal potential for L equals 4 must be balanced by a strong Coulomb attraction, so that paradoxically, a strong repulsion gives a very compact small radius shell. And therefore, the R max is small. And here, the vertical axis is the radius of maximum electron density. And you see it's clearly below 0.5, clearly below 0.5 atomic units. And these are the black squares for 5G. So you could call these 5G elements super lanthanides, because lanthanides have a very small, compact 4F shell, and here the 5G shell would be even more compact, even smaller, magnetic, but hidden deep inside the atom. So it would be quite a peculiar structure, and moreover, you would have quite many other valence orbitals. So summarizing what we can say about the periodic table, when proper tests can be carried out, and I refer to the gold atom or the small gold molecules, there doesn't seem to be any room for extra physical terms in chemistry, and in that sense, quantum electrodynamics was the last train from physics to chemistry. And then what I didn't say yet is that the chemical and physical differences between periods 5 and 6 seem to come from relativity. And in that sense, we can't expect new physics in chemical systems, but there will be numerous spin-orbit coupling effects in material science. So you can still discover new phenomena and new substances with some new mechanisms. We are not finished. Some people get scared when I say that QED was the last train from physics to chemistry. And the bottom line in the middle of the picture is that the periodic table, which I proposed in 2011 for Z equals 1 to 172, is not completely wrong. And the latest study found the 5G occupations, the purple straight line, which I showed. And we had some very good results by other people from including QED for small systems. And I say a second time, people are doing many further QED tests on hydrogen molecules and other light systems, notably in Poland. Then let's get back to Per-Olof Löwdin. People sometimes talk about the Löwdin doubling. And what if you, well, to begin with, you could call it a human right to make your own periodic table. So just go ahead and make your own if you are unhappy about the present one. And then if we take the S elements, or we take the P elements in the so-called left-adjusted periodic table, or we take the D elements, or we take the F elements, each of these is doubled. And that has been discussed in literature since Niels Bohr, including a paper by Löwdin in 1969, and there have been many, many others. And there may not be anything very deep about it because almost any screened Coulomb potential will work. So you could be fundamentalistic and take the Dirac-Fock-Bright Hamiltonian and do a very good, accurate calculation, or just take a Thomas Fermi potential or anything like that, and you still find basically the same answer. But it is an interesting question. If L2 means Löwdin doubling, why do we not have any L1s? Why do we not have any L3? And I have a modest answer to that question. So what drives the periodic table? If you take an H-like Aufbau principle, you would have the L1 case here, and this means that you would have one 2-electron row, then an 8-electron row, then an 18-electron row, then a 32-electron row, and so on. And that's what you find when you solve the hydrogen atom with a relativistic or non-relativistic for simplicity. And then if you take a real Aufbau principle for a screened Coulomb potential, then you find the red numbers in the right hand side with 2 times 8, 2 times 18, and 2 times 32. And now this is actually relatively easy to understand because we all know the hydrogen atom. So this means that you would effectively completely neglect electron-electron repulsion. And then we know that, yes, you can get an L1 periodic table if you completely neglect the EE repulsion. And that is quite unrealistic, but then you know what gives it. And similarly, as you see on the next slide, if you would strive after an L3 structure, then this means that you would have a 2s 2p, 3s 3p, and 4s 4p. So that instead of a chromium atom, for instance, you would have a 3d5 4s1, which is excited to a 4p5 4s1, and you can calculate the total energy using relativistic atomic programs for this process, and you will find that the excitation energy, which is the vertical axis, is over 10 atomic units higher. So you can have an L3, but it would be a very highly excited atomic state where the entire D shell contents have been raised to 4p shell. And then you know again why you don't have any L3 in the real life periodic tables. So the total conclusion is that the L2 Löwdin doubled periodic table has no plausible alternatives. And what sometimes is called the Conan-Doyle principle, if all other possibilities have been concerned, the remaining ones, no matter how improbable, must be right. And therefore, L2 is the only option that you would have left in your hand. Then the periodic table is a very rich structure, actually, with many different questions you can ask. And one such question is, should your lanthanide series or actinide series have 14 elements in them or maybe 15 elements in them. Personally, I prefer 15. And then if you take the last actinide, which would be Lawrencium LR, this has been predicted since Declos and Fricke 1980 to have not 6D 7s2 ground state, but 7p 1/2 7s2 ground state. And that has now been verified both experimentally and theoretically in a paper by Sato and others in Nature in 2015. But if you ask, is this chemically relevant, then the answer is no. With Xu Wenhua, we had a paper in PCCP in 2016 where we looked at the monocarbonyls of lutetium and lawrencium, and we also looked at hydrides and chlorides and so on. And then for these triatomics, the similarity of the top row and the bottom row is not a technical mistake, it's the message. Lutetium and lawrencium are so similar that you hardly see the difference in this picture. And therefore, it doesn't matter whether you start with a P1 atomic state or D1 atomic ground state. The outcoming molecular orbitals, for instance, at DFT level, here will still be very, very similar. And you can actually count from F0 to F14, which gives 15 elements, and leave some holes in the nominal group 3. So that's just one of the many questions about the periodic table, which is driven by the large gaps at the noble gases. And the 15 elements which I just talked about are mostly trivalent, and the simplest thing is to put all in the lanthanide group and to leave a gap below yttrium. And it's the same thing for actinium to lawrencium, and then thorium among actinides is usually put there, although the thorium atom ground state has no 5f electrons. And you could give a name to this phenomenon. The organesson, which is a noble gas, although it's not noble and not a gas, would have an anion. We found that it's the first noble gas which can have an electron affinity, which means that it can bind an S electron. And then you all know, as educated chemists, that lithium, beryllium, magnesium, or zinc would use the p orbitals, although the atomic ground state has no p's. And then, for instance, Rod Bartlett, who talked about alkaline earths, is hopefully aware of the availability of D elements, and thorium also can use some F character in its covalent bonds, although the F shell is empty in the atomic ground state. So you could introduce a concept of pre-S, pre-P, pre-D, and pre-F elements. And then a recent example by Gernot Frenking and the Chinese, reference 3, is an octacarbonyl of barium, which fulfills an 18 electron principle by using the d orbitals at barium. And for lawrencium, as I said, the chemistry is still trivalent despite of an atomic S2P1 ground state. Then I mentioned relativity, and we have effectively coupled Albert Einstein's special relativity to Dmitry Mendeleyev's periodic system, which we first did in a paper with Jean-Paul Declos, who recently died, by the way. The non-relativistic orbital energies of these diatomic hydrides are almost identical in the middle. So these two things are almost identical. These two things are almost identical. And then you have the relativistic stabilization of the gold S, 6s sigma, and the destabilization of the D and the concomitant Spinowitz splitting. Another neat example is the working of the lead battery, which is due to relativity. And here, about 1.7 to 1.8 volts of the 2.1 volt standard cell voltage comes from relativity. So older cars which use lead batteries indeed start due to relativity. And compared to thin relativistic effects, once again scale as z squared. The largest contribution coming from PbO2, and there also is some effect from the divalent lead sulfate. And then the QED work was done with Leonti Lauzowski's group in St. Petersburg, and they cancel about -1% of the Dirac level relativistic effects. And in that sense, the DFB Hamiltonian was 101% correct. These are the orbital energies as calculated in 1998. And the 1% is the difference between the relativistic contribution to the orbital energy shown here and 2 orders of magnitude further down to the Lamb shift given by the open squares. And then we have the Madelung rule, which maybe I don't have to discuss. Let me see. Mr. Chairman, how much time do I have?
Well, we actually are 3 minutes close to the ending of this session, but I give you a few more minutes and then we could have some questions.
Yeah, okay. And then the unexpected details of partial screening, I shall skip. And there is a recent paper which appeared yesterday in Chemistry, a European journal, issue number 1000 since the beginning. But that's about the 2s, 2p similarities. And I think I could, I'll stop here and forget about my reserve ammunition, which was not needed. So, questions?
Thank you very much, Pekka. Very interesting indeed. We have a few questions. Let me start with one from somebody who doesn't want to let us know who's asking it, who's saying, could you have L3 by increasing the strength of the electron-electron repulsion?
That's a good question, but how would you change, how would you increase the electron repulsion?
I think the one who asked this question asks about a virtual university where the natural constants are different.
Yes, yes. So that's an interesting direction to pursue. So if you had electrons with, say, charge 1.5 or charge 2, then what kind of a periodic table would you have? If you would play with the electron charge, it's a good question. I would say possibly.
Okay. There's another question from Sasong Ku, who asks how to configure the atom on the 5G group. I think you partially answered that, but please.
How would you consider the atom?
No, configure.
Oh, configure, I see, yes. I would use multi-configure, well, actually, it's extended average level. So one takes a certain spin orbit average, but uses, for instance, the p star and p, meaning p1/2 and p3/2 orbitals. So it's an average of the real relativistic orbitals.
All right. And may I wrap up with a final question from myself here? So as we develop the theory and start to include relativistic effects and QED effects, I'm sort of losing where are the potentials for development and improvement. Could you say something about what is the error due to that we don't exactly know how the Hamiltonian looks like? That what are the effects due to QED? And on top of that, from the sort of what we inherit from the non-relativistic part, what are the basis set effects and what are the effects because we're not making a complete CI?
Well, that's what I was trying to show with the atomic table for gold atom. So that gave the orders of magnitude. And then if you take the energy-related properties, IP and EA, you got about 1 per mil, roughly speaking, 1 per mil accuracy using the kind of basis sets, using pentupole excitations. And then our original purpose in the 1998 paper with Labzovsky was to find out is QED of any importance at all for the heavier elements, and that's the expression that Dirac-Fock-Bright is 101% correct and compared to relativistic effects. So then if I know the powers of 10, I'm reasonably happy.
Right. Thank you very much for an exhaustive answer. So with that, we close the first session of this symposium. I would like you to join me and thank Rod, Wolfgang, and Pekka for excellent presentations. Been very interesting. And as I pointed out, you can still post questions to the lecturers down in the Q&A. And I hope that the lecturers will try to go there and actually answer you in person. These answers are also going to be visible to all the attendees of the symposium. So now we're going to have a 1 hour intermission. Some of you are going to have breakfast. Some of you are going to have lunch. Some of you might get dressed or take a shower. So we'll see you again at 3 o'clock Central European time when we start session 2, where we're going to listen to Francesco Gianturco, Spiridula Matsica, and Sharon Hames Schiffer. So see you again at 3 o'clock.